Hi, welcome back. In this lecture, I want to talk about the phase QPU instruction. So the QPU instruction phase allows us to directly manipulate the relative phase of a qubit, change it to some specified angle. Like the Hadamard gate, the phase instruction, quantum gate, does not have any classical equivalent. So in the classical bit, we do not have a phase to change. The argument of the phase quantum gate is an angle, and is the angle we rotate the relative phase. So for instance, phase 45 denotes a phase operation that performs a 45 degree rotation. So what is the effect of phase quantum gate in circle notation? Well, as I mentioned in the lecture about circular notation, we just manipulated the phase of the state 1 with respect to the phase of the state 0. So the effect is simply rotate the circle associated with state 1 by the angle we specify. So in this case, for instance, is we apply to a superposition of a state, so this probably coming from a Hadamard gate, we know at this point. We apply to this qubit a phase quantum gate of 45 degree. This means that we apply a change of the phase only on the circle of state 1. So we operate a 45 rotation on the phase of the state 1. We note that the phase operation only rotates the circle associated with the state number 1. As other gates, we can express the transformation of this phase quantum gate using tensor metrics. In this case, we have, for instance, P, and then we have our angle, in this case, in radians. So we have like a 1 here. That also means that we are not going to change complex number that is relative to the state 0, but we only operate on the phase of the state 1. So to see the connection between rotation and exponential with a complex number, remember the Euler formula, that is this equivalence here. Together with the phase rotation in the literature, in other textbooks, you also note these other quantum gates, Z, S, and T, that are nothing else than a specialization of the phase quantum gate. So these are a phase with particular angles, pi over 2, and also pi over 4. So the Z gate is a phase with a pi as argument. The S quantum gate is a phase with pi over 2, and then T is our phase with argument p over 4. So you will always see this also in the literature. These are just a predefined phase quantum gate. So the effect on the Bloch sphere is just a rotation around the z-axis. So if this is the z-axis, it's just a rotation around here, right? And this say the angle. So remember that it doesn't change the probability of measuring one state over the other one, right? So remember that when we work on the Bloch sphere, the distance from state is 0 is basically the probability measuring in 0 or 1, and this transformation doesn't change this distance from state 1 and state 0. So this also means that it doesn't change the probability of measuring the qubit either in state 0 or 1. as all the quantum gates, so quantum gates are a unitary transformation that also by definition reversible. So phase operation are reversible. The phase operation might be reversed by apply a phase with a negative of the original angle. So we can rotate one, and then we take the negative and we rotate back. And this is actually the inverse operation of a phase, just change. So the Hadamard gate and the phase gate allow us to produce very, very famous single qubit quantum states that are also commonly used, heavily used in quantum computing. And for that reason, they get a special name, quite fancy name. So the first pair is this, plus and minus quantum states, and you see this is so this is just with the phase here, and then we have a phase that is rotated 180, and then also we have another pair of qubit state that is plus epsilon and minus epsilon state, and you see here we have the first pair plus epsilon is just relative phase of 90 degree, and then for minus y we have a relative phase of 270. So this is the last slides, and talk to you soon.